Start with a function f of x and define a region from a to b within this function. Then, set intervals within this region, label them x1, x2, x3, x4, etc. The greater the amount of intervals used, the more accurate the result will be for the area under the graph. Then, choose left or right. The distinction between either method will be discussed later. If you choose left, then draw a line at every interval, including x0 or a, up to where it meets the line of the graph f of x. Then, creating a rectangle using the line on the left as its height, and use the distance between each interval as its width. Now, we can use the basic formula for the area of a rectangle in order to find the area of any one of these rectangles. The width is equal to the distance between intervals, and the height is equal to the f of xn. For example, the area of the first rectangle is equal to the height, which is f of a multiplied by its width, which is x1 minus a. Hence, the area under the line, or the integral, of the line f of x within the region from a to b is approximately equal to the sum of all of these rectangles. This is how we derive the left Riemann sum. An example of the sum if we had 4 rectangles is shown. The area of the first rectangle would be f of x0 multiplied by x1 minus x0. The area of the second rectangle would be f of x1 multiplied by x2 minus x1, and so on and so forth until we had the area of 4 rectangles. And then we'd simply sum them up in order to find the area below the graph. Note that in any case, the more rectangles that we use, the more accurate our approximation will be to the actual area below the graph. I mentioned earlier that you can choose either left or right. If you chose right and not left, instead of using the left side for the height of the rectangle, you would use the right side of the interval instead. Most of the calculations will stay the same, except the formula for the Riemann sum will become this. The difference between the left and right Riemann sum is quite straightforward. In a function that is increasing, which means that the function has a constantly increasing gradient, the left Riemann sum will be an underestimate of the integral, whereas the right Riemann sum will be an overestimate. For a decreasing function, this is the opposite. Knowing how to perform the Riemann sum is all well and good, but why would you actually want to approximate the integral of a function? Well, for one, it could be the case that something is really complex or impossible to find the antiderivative of, such as these functions listed here. Or it could be that you don't actually know the equation of the graph itself. For example, data produced by equipment such as a seismometer